So far, we've been talking about gross AEP. Now, let's talk about most of the line items that separate gross AEP from net AEP. And these are the losses. Note that these are multiplicative losses. So if I take our engineer's number and we just say 1 minus that for each of them, at the end, the product shows what we have left. That's before erosion. Now, Gavin, let's talk through some of these wake losses. Here's a widely distributed photo. What makes these wind wakes stand out in this photo?
So really, it's just the turbulence that's created from each turbine being downwind of the one in front. There's a kind of accumulated turbulence after the wind passes through every turbine, and effectively, that's what you're seeing. It's the pattern of the wind distortions.
So basically, the guys in front are grabbing from the guys behind. Speaking of which, I found this video, and I kind of get it, but I was wondering if you could tell us for sure what it means. What are we looking at here?
So yeah, this is a really cool video. So what you've got two sets of wind farm layouts shown here. The one on top is a baseline, where there's not really been any deliberate attempt to optimize things. And then the lower one, where they've tried to optimize wind farm layout. And when we're talking about optimizing here, we mean minimizing wake losses. So as you can see in both videos, you've got red around the wind farm, which is where the faster wind speeds are.
You mean the one surrounding the leading turbine, right?
Yeah, exactly. So you can see that the undisturbed areas on the sides, that's where there's no turbines, they're fully red. And as you said, this is really crucial actually. At the head, or the front, the first turbines at the bottom of each video, there you're getting the full impact of that great wind speed. And then you've got a bit of red behind them, and then as you go back further and further through the line of turbines, it's getting more and more blue. So that means lower and lower wind speeds. But you'll see that that channel of blue is thinner in the bottom video, where the wind farm site has been optimized to try and minimize those wake losses.
So these guys, they're getting robbed in broad daylight. You can see how much wind energy is being stolen from them. Whereas here, they've thought about it more. I really do like this video because it shows the cumulative progress as well as the moment-to-moment improvement.
Yeah, that's right. I think showing it quantified in this way is really, really crucial, because it lets you see just how much is to be gained from doing that optimization. You know, it's not a case of just tinkering around the edges. You can see that moment to moment in that bottom right chart, as you said, you've got quite a large variance there. And then as that accumulates over time, it shows you that it's worth putting in extra time and expense on expert advice to do more optimization work up front to maximize your AEP.
So students, as much fun as we've had playing with our wind speed distributions and picking the best turbines, we have picked the best turbine for our case study, assuming it was only one. But then comes the detailed work of working out what kind of losses the entire farm will suffer when you've got a pack of them together.
So from that video, we've started talking about layout optimization. And so I think it's worth just dwelling a little bit on what that means in a practical sense. So what we're showing here is a very, very high-level schematic for an offshore wind farm. And hopefully you'll recognise what the key components are. But what I want to focus on is the left-hand side of this diagram, where we have the wind turbines and inter-array cables. So what can you see here? Well, all the black dots, these are turbines, and the lines in between these are the array cables. And I guess, just in terms of terminology, so turbines joined together by array cables are called strings. So all the strings here are all shown horizontally. And each string in this example has 7 turbines on, and then between them, strings have a certain distance between them. And our rule of thumb when modelling would be that you would have, say, about 9 rotor diameters between each string, and within each string, we would generally look at 5 rotor diameters between turbines.
5, wow. Do you recall what was the diameter for our chosen 10 megawatt turbine?
Yeah, for that, we're looking at a rotor diameter of about 193 meters.
Wow. Okay, so double the radius. 5 diameters apart. 960, so a kilometer apart. And we're looking at 100 of these guys. I guess they'd be arrayed in, I don't know how many rows we're talking about, but still, this is quite a distance covered here. I didn't realize.
Yeah, that's right. You would maybe have 5 turbines in a string, so that's a 5 kilometer long string, more or less. And then if you have that, you would be looking at, say, 20 strings, 2 kilometers apart, so 40 kilometers in breadth. So yeah, looking at something like a 200 square kilometer wind farm. And then, of course, you'd have an exclusion zone around that where you don't want any vessels or other traffic coming. So offshore wind farms are large.
Do we sometimes then see trade-offs whereby, in order to reduce wake losses, you increase spacing and therefore some other kind of costs go up?
Yep, that's correct. And so the optimization exercise is not merely about figuring out how you can minimize the wake losses, because if you take it to its natural extent, you would just put the turbines very, very far apart. So the optimization is very much a cost-benefit analysis, as you've just described.
So I think to optimize layouts, as we saw in the previous video, basically would require the economists or whatever you call yourselves in windy land, and the engineers and the resource estimate people to effectively be joined at the hip and engaged in this ongoing iteration.
Well, that's right. And to be honest, the tools that can do that all in one place are still evolving. You know, we've moved from a place, say, 5 years ago, where actually these separate disciplines would kind of feed into, their outputs from simulations into a central place, and someone would be trying to bring it all together and probably having to run many, many different cases, like different combinations, to see which one gives the lowest. But now we're moving to a world where people are developing smart tools that can handle all these different inputs at the same time.
We'll save that for the next course. Obviously, we're not doing anything like that here now, but again, we want to remind you of some of the simplifications in the model.
And in addition to layout optimization, one of the other key things that people are looking at to minimize wake losses is something that we talk about called total wind farm control. And what that means is, well, at the moment, the main way of controlling turbines is you have a controller within each turbine in the nacelle, and from there, from the onshore base, you send a signal to tell it to yaw to one side, like to change the direction in relation to the wind. And one thing that people are looking at is tools that can not exactly let the turbines talk to each other, but the controller will know what the overall impact is. So rather than trying to maximize the output from an individual turbine, you look at what the turbine yawing and direction is on a wind farm level. So you're trying to optimize the overall wind farm turbine directions to make sure you're maximizing your input depending on slight changes in direction and speed of the wind. So this kind of whole wind farm control, rather than individual turbine control, is another development that hopefully is going to eke out a few more percentage points of AEP.
Well, it makes a lot of sense. I could have told them they should have done that, but they didn't ask. No, a terminological note, yawing, as Gavin mentioned, is basically the turbine looking left or right, adjusting the direction in which it faces in order to catch wind from changing directions. Okay, so that takes care of wake losses, which is the big one. What about some of these others?
Yeah, so let's go through these one by one, starting with turbine downtime. And so as it's shown here, as expressed by the engineer, the 2.8% downtime, its inverse, which is shown in the next column, the 97.2%, that's what's called the turbine availability. And the way that we would estimate downtime is to look at all the times in the year when the turbine is out of action, either proactively, because you're having to do some proactive maintenance or inspection, or reactively, to repair a fault.
So I guess the downtime would not include time when the turbine has been feathered or shut down when the wind speed is too high, because when the wind blows at those high speeds, it's blowing past the back end of our turbine power curve envelope. That sort of shutting down gets captured right there in the gross single turbine AEP calculation, resulting in 0 kilowatt hours of power at those high speeds. So this is downtime from other factors, is that right?
Yeah, that's a really good way of putting it. So this is really looking at your plant being available to generate.
And so what are some of these other types of downtime?
So again, it's really anything where the turbine is out of service because something needs to be repaired, or where you have to take the turbine out of service for an inspection, for example. And if you remember, we talked about major and minor repairs in a previous lecture, and so that would be a good example where a turbine might be out of action for days or even months for a major repair, while you're waiting to get a heavy lift vessel to come and replace a blade or replace a generator. And so you have to factor all these events into availability estimates, routine stuff, and major and minor repairs.